Welcome again. This is our third lecture in series of Introduction to Quantum Mechanics. And today we will be discussing a very important problem called infinite square-well potential. So what we did in the last couple of lectures, in the first lecture, we looked into the experiments that led us to the development of quantum mechanics. And in the second lecture, we postulated a Schrodinger equation. We introduced the Schrodinger equation, and this is the equation that is due to Schrodinger. And what it does is that it gives us the waves that are associated with the particles. It describes those waves, and so it's a kind of wave equation for the particles. So since we learned that particles are associated with waves, and this equation tells us how the waves that are associated with the particle control the behavior of the particle. And then we said that in cases when the potential is independent of time, we can separate the time and space part of the wave function. So wave function is something that is waving in case of particle wave one. Waves that are associated with a particle. So this is the wave function for that wave. So normally, a simple idea that you can take up is that if we are a vibrating string, then the displacement is yxt is the wave function, and for particles which are moving, the psi xt is the wave function. So that's how we can correlate the two ideas. So what we said in our previous lecture is that in case v is independent of time, then solving this equation is not that difficult, because we are able to separate time and space part of the wave function, and we assume that the wave function is the product of space and time wave functions, and that's what we did in the last lecture. And then we came up that this is the equation we should solve for in case of time independent case of potential. Whenever potential is time independent, we'll solve time independent Schrodinger equation, and then the final solution will with time dependence will just multiply with the phase factor e to power minus iet by h bar. So psi x e to power iet by h bar represents the final solution. We also said that the wave function has to satisfy certain conditions, and those conditions are that wave function must exist and should satisfy the Schrodinger equation, that wave function and its derivative must be continuous, that the wave function and its derivative must be finite, and it should be single valued. Both the derivative and the wave function must be single valued, and wave function should also be a square integrable, and that demands that psi x should go to 0 fast enough as x goes to plus minus infinity. So this is the problem that now we will solve in the light of this wave equation. So we'll see all the features in this problem. So this is what we call as infinite potential problem. So we can have a classical realization first before we actually see the quantum mechanical features of the problem. The classical realization is that you have a, say, a small bead which is attached to a frictionless wire, and the wire is connected to two walls, two hard walls, and the bead can move to and fro between the two walls. Now, since the bead will bounce back at the walls, the bead is confined within the walls, the bead is free within the walls to move. It has zero potential within the walls, but since it bounces off at the walls, suddenly experiences a very, very large force, we say that at the walls the potential is infinite. Such a problem is said to be technically called as infinite potential well problem. Now, what is the quantum mechanical realization of the same problem? We have an electron that is free to move between two grids, this grid and this one. So let me explain what is this arrangement. You see there's a cathode and a grid here, and this cathode is at a very large negative potential. The grid is at zero potential because it is grounded, right? The potential only exists between the grid and the cathode. Again, on the left side, the grid is again, it is grounded, and the cathode is at negative potential. So the grid is at zero potential. So there is no potential that the electron will experience between the two grids. But as the electron will try to pass through the grid, it will experience a negative potential that will push it back into this region. Again, on the left side, if the electron will pass through the grid, it will experience a negative push that will push it back into the region between the two grids. So this is a very close approximation of an infinite potential well. So what we can do is that we can make this potential very, very large, so large that it almost is like an infinite potential. So then I can actually show you the graphical representation of the potential. In case the potential between the grid and the cathode is not that large, we can see it's a steeper hill here, a small hill that the electron will face. And if it has a very large energy, it can actually touch the cathodes. But in case that potential between the cathode and the grid is very large, then you can see that it will almost be like an ideal potential well. So this is actually the graph of an ideal potential well, where the potential suddenly goes to infinity at x is equal to 0 and at x is equal to L. And if the potential between the cathode and the grid is made very, very large, and the distance between the cathode and the grid is made very small, then very approximately, very, very closely, you can see that there is a close correlation that it almost represents your infinite square well problem, which almost matches with the ideal case. So now our problem is that another way of realizing this infinite potential well problem is the electron in a metallic wire, which is very thin, because inside the metallic wire, the electron is free to move, but it cannot come out at the ends of the wire. So at the ends, it is facing a huge potential, and it can always be restricted. Its motion is restricted within the wire. So that is actually very close example to the infinite potential well problem. We will actually do some problems related to this kind of arrangement. Now, how would we treat this problem? So first of all, we can have a direct treatment. What we will realize is that you can directly take the de Broglie approach. You can take the de Broglie condition that the particles are associated with the waves, and those waves, when they're confined between two walls, they can form standing waves, and this would give us the quantization of energy. Like we got the quantization of energy for these stationary waves in an atom. So we got that angular momentum quantization if you put the de Broglie postulate and say that only those orbits are stationary for which these waves make stationary waves. So if we put that postulate here, we can say that lambda by 2 is the distance between two nodes, and that their integral multiple would be the total length between the two ends of the potential, and that n takes only 1, 2, 3 values and so on, integer values. And since there is the non-relativistic energy momentum relation, and there is a de Broglie postulate for which momentum can be replaced by algebra lambda, we can easily get energy in terms of these constants, h square, 8mL square. So this is the quanta of energy, or the what we call as 0 point energy of the system is h square by 8mL square, and the higher energies would be the integral multiples of n square. So maybe the next energy is it would be 4 times this particular bundle of energy. The next would be 9 times the basic energy, and this what is called as the ground state energy, and so on. So in general, the energy is quantized, and there is a 0 point energy, the minimum energy that the particle has to have. It cannot be addressed. That's what we get if we directly apply the de Broglie postulate and assume that there are stationary waves which are formed between the two ends of the potential. What is wrong in this case? Now, the question is, what is wrong in this case? But it does not give us the complete picture of the particle in the potential well. That is something which we want. And this kind of approach, do you remember that in my first lecture I said that this kind of approach, Debye remarked that was a rather a childish approach. If we want to properly deal with waves, one had to have a wave equation. So therefore this approach is rather not very concrete kind of approach. To have a proper approach, we need to solve a wave equation, and that wave equation was proposed by Schrodinger. So now we'll try to get the same answers and much more using the Schrodinger wave equation. So this is what we need to now solve. We need to solve now Schrodinger's wave equation. Now you can see that since the potential is not dependent on time, the Schrodinger time independent potential, independent wave equation is this one. This we already know. It is minus h cross square d to psi of x by dx square to m factor here plus vx psi of x is equal to e psi of x. All I need is to solve this very equation. Now I will now impose boundary conditions and I will look at what kind of potential I have in order to solve this problem. Now we have the potential between the slots is 0. So V is 0 between the two boundaries, fine. So V is 0, fine. But the problem is that V becomes infinite at the boundaries. So if V is infinite there, then there is a singularity in this equation. There is a problem in this equation. So how would I remove that problem? I will take psi of x. It has to be finite. I will take it 0 at the boundaries. And if I take psi x 0 at the boundaries, then I can remove the singularity and at the boundary. So therefore, the wave function, should be 0 at the boundary and beyond the boundary, because beyond the boundary there is no possibility of finding electron there or finding a particle there, because the particle bounces between the two walls. There is no probability of finding the particles there is no probability of finding the particle here or finding the particle here. So that is not possible. So what we have is now that the particle is confined only between the two walls. Since the particle is only confined between the two walls, therefore particle is only confined between the two walls. Therefore, therefore we choose V is 0 between the two walls and psi of x is 0 at the boundary. So that reduces this equation to a very simple second order differential equation, which is minus h cross square by 2m d2 psi of x dx square equal to e psi of x. So this equation we need to now solve. Since it's a very simple second order differential equation and solving it is very simple, very trivial. So what we do is now we solve this equation. So we look for the solution to this equation and we assume that twice me by h cross square is k square. So I assume this factor twice E by h cross square is k square, but twice me, is p square, momentum square, because E is p square by 2m. So the root of this is momentum, square of this is 2me. So k square would be in terms of momentum as p square by h cross square, or p by h cross whole square, which would still be equal to k square we know is twice me by h cross square. So it's nothing but just telling you what the k simply means, what the k simply is. So k is actually, if I put a de Broglie postulate here, it's a wave number, simple wave number, because for de Broglie postulate, p is lambda by h by lambda. So then h and h factor will cancel. So it is 2 pi by lambda, which is actually a wave number. Now, the solution of this wave equation, we already know it, right? Or you can actually figure it out. It's not a big deal. Its wave equation, its solution is psi of x is equal to a sine of kx plus b cos of kx. That is the solution to this equation. Okay, so then, we will try to see whether this solution, it satisfies the boundary conditions. So we'll see whether this satisfies the boundary conditions. Fine. Going to be a little bit more mathematical now. So you see that if I put this x equal to 0, so I am on this first wall. So if I put this x is equal to 0, these were my 1 minute, excuse me. So, sorry. So, 1 minute, there is some problem. It's not writing. Okay, anyway, so this b of cos of kx, if x is equal to 0, then you will see that psi of x will not be 0 because cos 0 is 1. So there I will be left with b. And that I don't want. I want psi x to be 0 at x is equal to 0. The only way that can make sense is that b is 0 all the time. So I choose b as 0 so that it makes sense. So I choose b as 0. So if we choose this b as 0, then it will be psi x will be 0 at x is equal to 0 because sine 0 is 0 anyway, right? So therefore, choosing that psi of 0 is 0, it has to be 0. So demands that b should be 0. So we get rid of this term, we get rid of the cos term. So we are only left with the sine term. So now the wave function is very simple. It is just psi of x, a sine of kx. Now it needs to satisfy the other boundary conditions also. So what is the other boundary condition? Other boundary condition is that when x is equal to L, the wave function should be 0. So the other boundary condition is that, go to the next slide. So now we say that when x is equal to L means here the wave function should again go 0. That is our demand, fine. So we say that at x is equal to L, the wave function should again go to 0. So that means a sine of KL should be 0. That means KL should take values when sine should be 0. And that means KL should be n times pi. If KL is n times pi, then and only then the wave function would vary whenever psi is equal to L. So we have Kn is equal to n times Kn would be, since KL is n times pi, so K would be n pi by L. So if K is n pi by L, we know how K is related with energy. The energy quantization is easily figured out. Energy quantization is that the energy of the nth state is n square E1. Now the question is why we should take n from 1 to infinity, 1, 2, 3, and so on. Why not n equal to 0? Now remember that our wave function psi is equal to a sine of k of x, fine. And for k now I'm substituting n pi by L. So if n is 0, then it doesn't matter where you are. X equal to, it doesn't matter what the x is. Psi will be all times 0. That's nonsense, because if psi is 0, it means particle is not inside the box. Therefore n equal to 0 is not taken. So that's why we don't take n equal to 0. Then you can also say that why n is not -1, -2, -3, because minus values, minus n pi, sign is again 0. Why we don't take minus values? The reason is that because if you take a sign of say minus n, okay, and some factor say x, okay, so that would be equal to, it will be equal to minus times sine of nx. It will be minus times sine of nx. So you get the same wave function, you get the same wave function, only there is a negative sign in the front. So you don't get anything new. So the minus solutions would be same as plus solutions. So you take only one of the solutions. And so that is why we restrict only to the positive values of the integer. We don't, we neglect the negative values of the integer chosen. So this is the reason that why we should take, you must understand things properly, and that why n is not 0, why n is not negative, because n is negative does not give us anything new, and n equal to 0 gives us the same thing which we get with n equal to, sorry, negative gives us the same thing which we get with n equal to positive. So therefore we keep only n as positive value, positive integers. Then other would be that we need to fix this a. The a is not yet fixed. We need to fix this a. That can be obtained by imposing the normalization condition. Since the particle is somewhere in this box, so somewhere in this potential well, so we say that between 0 to L, particle is suddenly there. So the probability, total probability should be 1, and that would fix, because sine square of theta, we know how to integrate it out. It's 1 minus cos 2 theta by 2. Just use that value and we figure out that sine of nx is root of 2 by L sine of n pi x by L. So we are able to get these wave functions. So we are able to figure out what are the wave functions for different values of energy. So for example, psi1, the energy would be E1, and the corresponding wave function would be root of 2 by L sine of pi x by L. For n equal to 2, the energy would be E2, which would be 4 times E1. That energy would be 4 times E1. And then the corresponding wave function would be root of 2 by L sine of n pi x by L. So we are able to obtain wave functions, we are able to obtain energies. And energies, again, you see that energy that we obtained here was the same that we obtained by just imposing the these standing waves, condition on standing waves between two ends of the potential. So, but here we are able to get wave functions, and we'll get much more using the proper analysis. Okay, then we can plot these energy values, and we can see that you can see the distance between the energy levels is increasing as n is increasing. But there are some very important points to note here, and one of the very important points to note here is that the energy, you can see the ground energy or the quanta of energy is pi square h square by twice L square. This is the minimum energy that is in the that the particle is carrying. So that means in quantum mechanical sense, the particle cannot be at rest. But in classical sense, the bead can be at rest between the two walls. But if we have a quantum mechanical version of the same problem, the particle cannot be at rest. So the reason is uncertainty principle. When I am confining the particle between two in some delta x, say L, so it has to have some momentum, and that momentum minimum should be of the order of h bar by L. So that momentum minimum should be of the order of h bar by L. And since it has minimum that momentum, therefore it has a minimum energy. And that minimum energy is pi square h cross square by twice ml square. Now the question is that in the classical mechanics, you don't have such thing. Why not? Because this L is very large, and you can see the value of h cross square also. H we know is of the order of 10 to power. It's of the order of 10 to power minus 36, and it is h square. So it is 10 to power minus 36 minus 36. So that is 72, I think. Huh? Yeah, so it is 72. 10 to power minus 72. How can we pick up that experimentally? So, but only if L is very, very small, it's of the order of 10 to power minus 15, minus 18 meters, then this problem makes some, these energy quantas, they become visible. So, but in the classical domain, the L is large and H is extremely small. The quanta of energy are so small that experiments won't be able to pick this up, and these quantum mechanical problems smoothly go to classical problems at large values of N. Now we can do one thing, we can plot all the wave functions and the corresponding probabilities. So let's plot now for n equal to 1. You will see that you will have, for n equal to 1, we can have this L equal to 0. This is a node here and a node here, and there is an antinode here. Fine, but what are the number of nodes for psi equal to 1? Remember, there are no nodes. Why? Because the nodes at the boundaries are not counted. We normally don't count these nodes. Only nodes between the boundaries are to be counted. But for n equal to 2, we have this. This is the graph for n equal to 2 for this wave function, and there is one node at n equal to 2. So n equal to 2, there is one node here, and that n equal to 3, there are 2 nodes. So the nodes are increasing regularly at 1, 2, 3, and like that, 0, 1, 2, 3. That's how the nodes increase. And you can see that with respect to the center, we have two kinds of, if we take the center, with respect to the center of the potential, the wave function looks symmetric or anti-symmetric. You can see the ground state is symmetric with respect to center, but the first excited state is anti-symmetric. So it is that it is a even odd functions are obtained with respect to the center, and you can see then the next is also psi3 is symmetric, and psi4 will be anti-symmetric. The probability is, if we see the probability density, and we figure out something very interesting, that the ground state, the particle is most likely to be found in the middle of the potential. Something very crazy, because remember that in classical mechanics, the particle is moving with constant velocity between the two ends, and therefore it has equal probability of finding it anywhere. The probability is same. But in quantum version, the probabilities are different. And you see, if you are in the next excited state, it has zero probability at the center. Something very amazing, and only possible in a quantum mechanical story. And again, you can see that when psi3 square is plotted, that probabilities are distributed in this manner. So this is, we get the sense of how the probabilities or probability distribution of the particle confined to a one-dimensional potential well can be obtained using Schrodinger equation. Then if the n is very, very large, if n value is, say, for n equal to 10, you can see the dotted line is the probability for classical case. You can see it is constant, but this is a probability distribution for n equal to 10 is plotted. But if n is, say, 100 or 1000, it will be almost smooth, and the average value would be the same 1 by L value. Then we can also see that we can write the complete wave function, since the time dependent part has this solution. So time dependent part we have already solved. The solution for time dependent part is e to power I omega t, or e to power minus I e by h bar into t. And therefore the complete wave function for the particle confined in a potential well is given by the time independent part, root of 2 by L sine of knx multiplied with the time dependent part. But then this time independent part, sine kx, we can write it in terms of these exponential functions, so that the complete solution is actually a superposition of two waves, one progressing in the forward direction, other progressing in the backward direction, superimposing, giving us the solutions that we have talked about. So this was interesting, I think quite interesting to look into the various things, various solutions of a potential particle confined to a one-dimensional potential, which is of infinite extent at the boundaries. So I think we are done with today's lecture, and then we can actually, I can encourage you to look for some problem solving, because that would actually help you for the better understanding of the subject. So a couple of problems that I will be interested with you is that you try these problems. They are very interesting problems. And these problems, I just will tell you what you have to do. So you see, the first problem is that an electron moving in a thin metal wire is a reasonable approximation of a particle in one-dimensional infinite well. The potential inside the wire is constant on average, but rises sharply at each end. Suppose that the electron is in a wire of 1 centimeter long. Compute the ground state energy for the electron. If the electron's energy is equal to the average kinetic energy of molecules in a gas at T equal to 300 Kelvin, about 0.03 electron volts, what is the electron's quantum number? This can be easily done. I mean, what you have to do is you have to use that energy relation, that's all, and figure out. The other one is also very easy. Find the energy in the ground state of electron confined to one-dimensional box. And here the length is large, it's 0.1 nanometer. It's actually large. You will see that. This box is roughly of the size of an atom. Make an energy level diagram. Then nice, find the wavelengths of the photons. You see, there are energy levels. Now, if the electron jumps from one energy level to another energy level, again, the emission of photon is possible, like in hydrogen atom. You need to figure out what is the energy level diagram, and that would be interesting, and please do it. And in our second lecture, now I conclude my second lecture. So in our second lecture, we have completed this problem of potential in one dimension, and we have taken infinite potential well problem, which we have addressed in this lecture. In the next lecture, we will have the finite potential well problem. And so we'll try to work on that. And remember also that particle in a box and potential, infinite potential well problem, it is the same. So where you sometimes people call it as particle in a box. So the curiosity has to continue, and finally you will figure out that curiosity will kill the cat. Okay, thank you and take care. Bye bye.